All right, everybody, welcome back. So last time we were talking about uncertainty in measurement. We were talking about some statistics. Uh, Going back to the uncertainty in measurement, we're going to move on to significant figures and calculations involving them. So significant figures are really where your uncertainty comes in. And so your significant figures are going to really dictate the reliability or the accuracy of your number. So there's a couple of rules for deciding how many significant figures a number has. So, of course, any non-zero integer uh, is significant. So if you look at this first one, 1,237, you count 1, 2, 3, 4. That's four significant figures. Here we have, then the next one is 87,467,332. We have 1, 2, 3, 4, 5, 6, 7, 8. And so that's eight significant figures. Numbers like that, pretty straightforward, pretty easy. But then we have to think about how to deal with zeros. There are three types of zeros when dealing with significant figures. There's leading zeros, and those are going to be zeros that are to the left of your number or precede non-zero integers. I've got to work on the typos. So are no counted, are not counted as significant figures. So if we look at the 0.002345, uh, this has four significant figures because we don't count those three zeros. And then we have 1, 2, 3, 4. Captive zeros. So those are going to be zeros between non-zero integers. And so if you look at this one, 2014.05, we have 1, 2, 3, 4, 5, 6, or six significant figures. So your captive zeros are always going to be significant. Now, trailing zeros can be one or the other. Trailing zeros are not significant unless there's a decimal point. So trailing, if leading zeros are to the left, trailing zeros are to the right. And so here, let's look at the 3.00. So there's a decimal point, 1, 2, 3. Three significant figures. Now look at this one, 120, but you notice how there's the decimal point on the end of it? That makes that zero significant. But let's go back to the 500 here. It's just 500 with no decimal point. So there's only one significant figure for that one. All right, so when we start looking at calculations, we'll have to figure out how many significant figures an answer is going to have. One thing to keep in mind, exact numbers are never part of the consideration for significant figures. Okay, so a lot of our exact numbers are going to be, we use them as conversion factors. So you see here, like 1 kilometer is 1.00 times 10 to the third meters, or 1,000 meters. That 1.00 is not going to contribute three significant figures to the to figuring out how many sig figs the answer has. The 1,000 won't either. Another conversion factor between like your English and your metric units is 1 inch equals 2.54 centimeters. Again, that 2.54 is an exact number. Okay, so you're not going to use that to figure how many significant figures you have at the end of a calculation. And there at the bottom, you see the equation for the circumference is 2 times pi times the radius of a circle. Well, that 2 pi, those are exact numbers. So again, they're not going to factor in. We want to make sure we know how to count the significant figures in scientific notation. And so here, if you see the 12.03 times 10 to the sixth, When you're counting the significant figures of scientific notation, you do not count the 10 to the 6. You just do your 1, 2, 3, 4. That's 4 significant figures. Again, the 5.6 times 10 to the negative third. You don't count the 10 to the negative third. And you're just going to have the 1, 2. So the 2 significant figures. You're only counting the number at the front. Okay, so there's a couple of rules for performing calculations. In addition and subtraction, you're going to round your answer to the number of decimal places that the smallest number has that is involved in your addition or subtraction. It's easier to get the hang of if we just look at it. So if we look at this first addition and we say, well, what is the answer going to be? I'll show when you add this all up, you're going to round it to 10.42. Now you notice that your answer has 4 significant figures. The way you round it is you look at all your numbers here and you notice your 0.34, that's 2 decimal places. 0.4021, that's 4 decimal places, and 0.679 is 3 decimal places. So you're going to round to 2 decimal places. No matter what your answer is, you're going to round to 2 decimal places. So if you look at the subtraction, you have 2 decimal places and 1 decimal place. So you have to round this answer. So this will be a negative 5.4. You have to round it to 1 decimal place because 1 is the lowest number of decimal places involved in your subtraction. That's how you do addition and subtraction. Multiplication and division is you're going to round to the lowest number of significant figures. So if you look at this first one, this multiplication, you have 4 significant figures and 3 significant figures. So I have to round my answer to 3 significant figures because 3 is the smallest one. Or I have the 5.6 divided by 2.034, 2 significant figures versus 4. 2 is the smaller one, so I have to round to 2.8. Now, I'm sure most of you have seen this before, but we're going to predominantly do division as a fraction. We're not going to really use the division sign you may have used in high school anymore. We're really going to stick to this fractional notation. Okay, so now when you're performing a calculation where you're going to combine, you're really going to wait till the end to round down to your proper number of significant figures. Now, you're going to want to maybe review your order of operations because when you look at this, you have 5.44 plus 8.9 divided by 7.332. Now, that parentheses means that you're going to do that addition first. Okay, when I do that addition, when I did it, my calculator gave me 14.34, 7.332. Now, you notice I didn't round that addition. If I had rounded that addition, I would have had to have rounded it to 1 decimal place because of the 8.9. But I want you to keep that in mind. So this is going to take some practice. Now, when I divide these two without rounding, I get 1.9558. Okay, now, how would I end up rounding this? Okay, so what I do is I say, if I was to round that 5.44 plus 8.9, that would have rounded this number to 3 significant figures. So technically that means I have 3 significant figures divided by 4 significant figures, which means that I'm going to have to round this final answer to 3 significant figures, or 1.96. Now, if you had rounded the addition before you did the division, you still would have gotten very close to the answer. You would have gotten 1.95 because you would have rounded this 14.34 to 14.3, and then you would have divided. And so you see that the proper rounding for the addition gives you 14.3. That's where the three significant figures comes from. That's why you round to 1.96 at the end. But you still end up slightly off. So it's best to keep track of what you would have done the whole way through, and then take that into account when you're counting the significant figures you have to round to at the end. So it'll just take some practice. So let's look here. Let's perform the following calculations and express each result with the correct number of significant figures. Okay, so we have 3.25 times 10 to the third plus 6.174 times 10 to the second. This is an addition, and I have 2 decimal places and 3 decimal places, so I have to round to the 2 decimal places. And when I add this, first off, I'm just going to add it up. I get 3.8674 times 10 to the third. And when I round this now, I get 3.87 because I have to round to 2 decimal places times 10 to the third. Now, part B, I have 0.102 times 0.0821 times 273 divided by 1.01. Now, what we're going to do first is we're going to multiply the top. Okay, so when I multiply the top, I'm going to get 2 point, and I'm just straight multiplying without rounding first. 286,157 over 1.01. And now when I divide that, I'm going to get 2.2635. Now the question is, what do I have to round that to? Okay, so look at the top. Each one of those is only 3 significant figures. Again, forget those leading zeros. You have 1, 2, 3. Forget the leading zero. 1, 2, 3. 1, 2, 3. These are each 3 significant figures. So if I was to round that multiplication before the very end of the problem, this top number would have had to have been rounded to 3 significant figures. So then technically what I have is I have 3 significant figures divided by 1, 2, 3, 3 significant figures, which means I have to round the answer to 3 significant figures. So 2.26. So you have a rubric for your assignments. Make sure you're following that. On some problems, you can't actually fulfill the entire rubric. So something simple like this is just a straight calculation, straight answer. You go ahead and you just do the straight answer. You still put in as much detail as you can, but the whole rubric is really for when you're going to be answering exercise, working through exercises involving like full chemical systems. You'll get used to it as time goes on. Okay, so the last one we have 6.404 times 2.91 divided by 18.7 minus 17.1. So we're going to take care of both parentheses first. When I multiply the top, I get 18.63564. And when I subtract the bottom, I get 1.6. The bottom just happens to work out to the proper decimal places. Okay, and so let's see. We say, well, which one's going to dominate? Okay, well, if I was to round that multiplication on top before I get to the very end, you notice I have 4 and 3 significant figures. This top number would technically be 3 significant figures. The bottom, again, it just happens to work out, but if you were to, so you don't even need to round it, so you get 2 significant figures. So I have 3 divided by 2, which means my final answer is only going to be 2 significant figures. When I divide this, though, I get 11.6, which is 3 significant figures, which means I'm going to have to round to 12. Okay. Dimensional analysis. So this is one that I would really try to get used to. You're going to be using this a lot. So in chapter 1 here, it's pretty straightforward. Uh, we're going to be setting up calculations where I call it chasing units. So you have a number in certain units, you want it in other units. So you're just going to keep using conversion factors until you get to the units that you need. Also, something to keep in mind, when you're using numbers in their units, the number will always go with the unit on top. So here you have, and this will become a unit that's very familiar to you. You have 12.01 grams per mole, which of course we talked about that. That is the mass for carbon, 12.01 grams per mole. But if I was to write this as a conversion factor, you see that the 12.01 goes with the grams and then it's per mole. Okay, so just kind of keep that in mind when you're trying to figure out how to put these conversion factors into calculations. So let's look at translating certain units. Okay, so convert 154.2. Now remember your mu here, that Greek letter mu, that's micro. 154.2 micrometers to millimeters. Okay, so in this one you can kind of start to follow the rubric. So what is the exercise asking us? That's what we're being asked for. What is this in millimeters? Okay, what are some things that I know? Well, I need to write down my list of things I know. So these are going to be conversion factors. 1 micrometer is going to be 1.0 times 10 to the negative 6 meters, or over here, there's your micro. Now remember, I'm going to use it. I'm going to use this conversion factor in this format. Remember, you can always flip this. Nope, not negative. You can also do it that way. It's the exact same thing. It's just you flip the 10 to the 6 to the other side. I'm going to use it in this format. So, what's something else that I know? 1 millimeter is 1.0 times 10 to the negative third meters. So again, there's your milli, there's your 10 to the third. So I pulled those out. Now, here's how I set it up. I use what I call the train track method. So I'm going to start with what I have. My 154.2 micrometers. Okay, now I need to put my conversion factor in here in a way that cancels out micrometers. Well, if I put micrometers on the bottom now, then micrometers will divide out. So if I put 1 micrometer is 1.0 times 10 to the negative 6 meters. And now I want to get rid of meters to go to millimeters. So that's where I have my second conversion factor. Okay. And the way this works is everything across the vertical line is a multiply. Everything across there is divide. So the horizontal line is divide. So that means micrometer divided by micrometer cancels. Meter divided by meter cancels. And now what I'm going to have is 1.54 times 1.0 times 10 to the negative 6 divided by 1.0 times 10 to the negative third. And so what this is going to give me, let's see, what do we have here? 0.1542 millimeters. Now, is that in the correct number of significant figures? Well, you notice that your 154.2 is 4 significant figures. And everything else is an exact number. So I don't even worry about those. So since the only number that matters as far as counting significant figures has four significant figures, my answer has to be in four. Now, that's the way I do it. I walk it through, I start and I get all my conversions for different units to meters, and I walk it from micrometers through meters and then to millimeters. You can also just go straight to millimeters if you know how. So let's look at a ratio. So I could take a ratio between my micro and my millimeters. So that's my ratio. And what this is going to mean is then I can multiply through by the 1 millimeter, and I'll get 1 micrometer is 0.001 millimeter. Now I can use that as a conversion factor, and I could just start with saying, well, 154.2 micrometers. And then I can say, well, my conversion factor, I need to get rid of micrometer. So I'm going to put it on the bottom, because now you notice micrometers divided by micrometers cancels out. So that unit is gone. And I have 0.001 millimeters. And when I multiply this up, I get 0.1542 millimeters. Okay, so I use the train tracks. Maybe you saw your teacher in high school do it this way. You could just start with your 154.2 micrometers. Then I'm just going to multiply through by all my conversion factors in the proper, having them flipped around in the proper way to cross out the units that I'm trying to get rid of. So then what? We have 1.0 times 10 to the negative 6 meters. One micrometer, and then 1.0 to the negative third meters, 1 millimeter, and that's going to give us our 0.1542 millimeters. And in this case, what we did was we just replaced these vertical lines with parentheses. So compare this one, can compare this last expression to this first one we did, and you'll see that they're exactly the same. It's just we replaced the vertical lines with parentheses. And so you notice here, micrometers divided by micrometers cancels that out. Meters divided by meters cancels that out. And I'm left with the only unit I have left is millimeters. And that's what I was trying to calculate to. Uh, this is going to be a type of calculation that you're going to do a lot. You just want to make sure that you're thinking in terms of multiplication and dividing. Um, and so really you just think about it. When you want to get rid of something, you divide by it. So the way you can think of it, like when I say micrometers divided by micrometers, that's the same thing as saying, well, what happens if I do x divided by x? They cancel each other out and you get 1. What if I have y times x divided by x? Well, x divides out x and you just end up with y. So it's the same kind of math. So here's one. Convert 2.46 times 10 to the sixth. Oh, here you go. Cubic nanometers, and convert that to cubic meters. This one can get a little interesting if you're not quite sure what you're doing. So let's take a look at it. So, according to the rubric, what I want to know. So I want to know that there's not really any theorems to write down. But I do have things that I know. So I can say, well, I know that 1 nanometer from my list up there is 1.0 times 10 to the negative ninth meters. But I need a conversion for cubic nanometers to cubic meters. How do I do that? Well, here's how I do it. So what I'm going to do is I'm going to take that conversion factor. And so I'm going to box this off. Those are the things that I know. And I'm going to say, well, 1 nanometer cubed 1.0 times 10 to the negative ninth cubed. And here's the math that you're doing. Let's say I have x times y squared. That squared distributes. So I'll get x squared times y squared. That's what I'm doing here. Okay, so this will be 1 cubed cubic nanometers 1.0 times 10 to the negative ninth cubed cubic meters. So these are the units that I need. Well, 1 cubed is just 1 nanometer cubed. Now, this 1.0 times 10 to the negative ninth cubed becomes 1.0 times 10 to the negative 27th cubic meters. There's my conversion factor to go from one cubic number to another. And you can do this every time you have to do this kind of calculation. You can just walk it through these steps and make sure, so you just want to make sure you're getting the proper conversion factor. And so what we have is we're going to have our 2.46 times 10 to the 6th cubic nanometers. And cubic nanometers needs to be canceled out, so that unit needs to go away. So I'm going to put 1 cubic nanometer on the bottom so that cancels out. And my conversion factor is 1.0 times 10 to the negative 27th cubic meters. And when I multiply this out, I am going to get 2.46 times 10 to the negative 21st cubic meters. Again, that three significant figures on the 2.46 is the only number dictating how many significant figures my answer gets. Because this, the 1.0, is exact, so we don't use it to count. Now this is something I will rarely do to you in problems because I don't like it. You, I just don't know too many places in a scientific career where you run across this. Engineering a little more so because engineering will have some English units, but otherwise. But let's convert 65.1 miles per hour to kilometers per second. So this will be a little different because you see here now, here we have fractional units, miles per hour, kilometers per second. Okay, so remember what we said, the number goes with the unit on top. So like your 65.1 miles per hour is actually 65.1 miles per hour. Okay, so what are we being asked? Kilometers per second equals what? Uh, and then of course there's some conversion factors that you can walk through any conversion factor you remember. The one that I've used a lot that I just happen to remember is, so I'm going to write down 1 inch is 2.54 centimeters. You may know how many meters are in a mile. You may know how many kilometers are in a mile. You may, whatever conversion factor you can remember, go with that one because it will help you get to places, get to things quicker. Uh, and then of course, 60 seconds is 1 hour. No, nope, sorry, is 1 minute. 60 minutes is 1 hour. These are all things that I know. Let's see. Kilometers. I know that there's 1,000 meters in a kilometer. You can do that. I also don't mind if you do. I don't care if you do that one. It's the same thing. And I also know that there's 100 centimeters in a meter. I don't care if you do the 1 centimeter. There's 1.0 10 to the negative second meters. Again, I don't care. Use the format you're comfortable with. But these are things that I know that are going to come in helpful. Now, you can do this calculation 1 unit at a time. Okay, so let's do kilometers or miles to kilometers first. Okay, 65.1 miles per hour. Okay, something else that I need to write in here is there are 5280 feet in a mile. Okay, so since I know that I set this up this way because the conversion factor I remember is the 1 inch is 2.54 centimeters. So I'm going to work this through that conversion. Again, you can work it through whichever conversion you remember. So this means that I have 5280 feet in a mile. So now mile divides out. So now I have feet per hour. Let's see. 12 inches in a foot. Yep, okay. So there are 12 inches in 1 foot. Feet divide out. And you see, I try to make sure I add everything to my list of known quantities. So even all my conversion factors. Now I have inches per hour. So now I can use my 2.54 centimeters in an inch. Inches divide out. So now I'm in centimeters. And then, of course, like I say, there's 100 centimeters in a meter. Centimeters will divide out. And I have meters per hour. Because you notice I haven't touched the hours unit yet. And then, of course, there's 1,000 meters in 1 kilometer. Okay, so meters divides out. And I'm going to have kilometers per hour. So again, I'm going to do 6.51 times 5280 times 12 times 2.54. And then, of course, these others are just 1 and 1. Okay, now, across the bottom, I have ones. Then I'm going to have 100 times 1,000. And once I multiply up the top and I multiply up the bottom, then I'm going to divide the top by the bottom. And when I do that, this will be 105 kilometers per hour. Let's see, the significant figures were dictated by the 65.1 at 3 significant figures because the rest of the numbers are exact numbers. Okay, so now I have kilometers per hour. I want kilometers per second. So now I can just work on the hours. All right. So I know that there are 60 minutes in 1 hour, and there are 60 seconds in 1 minute. You notice that hour divides out hour, minute divides out minute, and you end up with kilometers per second. And it's going to be 105. Across the top, it'll be 105 times 1 times 1. And across the bottom, it'll be 1 times 60 times 60. Then I'm going to divide the top by the bottom. And so 105 divided by 60 times 60 is going to end up giving me 0.0292 kilometers per second. So there's the answer to my conversion. Now, I split this up and did each unit separately. You can do that. That's fine. You can also do them all at once. Okay, so let's see if we can do. We can just take this and turn it into one big long grid. Okay, so we'll start back with our 65.1 kilometers per hour. Okay, so 5280 feet. And hang on. Sorry, use the wrong unit here. 65.1 miles per hour. So it's 5280 feet in a mile. Miles are gone. And again, I'm just using the conversion factors I remember off the top of my head. You don't have to use these exact same conversion factors. Just make sure you write down what you use in your known quantities at the top of your solution. Let's see. I need to get rid of feet, so 12 inches in 1 foot. Feet divide out. Okay. 2.54 centimeters in 1 inch. Inches divides out. And then I have my 100 centimeters in a meter. Centimeters divide out. Up to meters per hour. Let's see. And then 1,000 meters in a kilometer. So now I've taken miles to kilometers, which is what I needed to do. So I can stop there with the distance. But then I'm just going to add that 1 hour is 60 minutes. So hour divides out with hour. Let's see, 60. Not minutes. We already did that one. 60 seconds in a minute. Okay, and so then minutes divides out minutes, and we are up to kilometers per second. And when I multiply this all up, I get my 0.0292 kilometers per second. And so, of course, the way I would do this is 6.51 times 5280 times 12 times 2.54 times 1 times 1 times 1 times 1. Again, anywhere you don't see a number, there's a 1 there. First is on the bottom. I have 1 times 1 times 1 times 1 times 100 times 1,000 times 60 times 60. And then once I have all those multiplied up, Then I'm going to divide the top by the bottom, and I get my final answer. Okay, so now I prefer just doing the one long grid. Uh, I don't care if you break it into multiple tiny grids, you do it as one long grid, two medium-sized grids. I want you to solve these problems how you're comfortable, but I want to see every single step of your process. Okay? When I say if you use AI to help you on something, again, which I suggest you don't do, because you want to make sure you're activating every part of your brain when you're training on how to solve problems. That way you can recall how to do it again later. But when I say that you have to translate whatever AI gives you into the theory that's either in the textbook or that I give you, that would mean like you would take what AI is helping you with and you have to translate it into grid patterns, large, big grids, small grids, medium grids, but it just has to end up matching this format or this format or whatever's in the textbook. Okay, so temperature. We're not going to do a ton with this. I just want you to know how it works. Mostly what you're going to be doing is converting Celsius to Kelvin. Uh, mm, mm, mm. Kelvin is where you do most of your work because that's the SI unit for temperature. So you're going to have to look at your constants. Every now and then you'll have a constant that would have Celsius in it. So you want to, and you'll see that one, well, in Chem 2, when we get to colligative properties and you have like, say, your freezing point depression of a solution. And so the constant for that's going to have degrees Celsius. So of course we have to leave the temperature in degrees Celsius. Otherwise, like when we get to gases, you're going to see your ideal gas constant has Kelvin units. So I always suggest just making everything match um, the constant. Also, since it's the SI unit, you can't really go wrong just uh, putting everything in Kelvin and going for it. I want to make sure you know how the formulas work. These are your conversion formulas. So that temperature Kelvin is your degrees Celsius plus 273. So if you wanted to change back, you just subtract the 273 for both sides, and your Kelvin minus 273 will give you back your Celsius. The change from Fahrenheit to Celsius, of course, now pay attention to your order of operations. Notice the brackets. That means you're going to do your temperature Fahrenheit minus 32 first, then multiply by the 5/9. Otherwise, if you want to change Celsius to Fahrenheit, you have this here. Want to make sure that your algebra is up to the point where you know how we get from one to the other. So it's like if I have, let's look at our temperature Celsius. And so how would I convert that to temperature Fahrenheit? Well, the first thing I'm going to do, you want to divide both sides by 5/9. Okay, so you know that 5/9 divided by 5/9 is 1. Now, I hope you remember enough about fractions to know that when I have 5/9 in the denominator, it's going to flip that fraction over. It's essentially like when you divide by a fraction, you flip it and multiply. So what you're going to end up with is 9/5 times Celsius is going to be temperature Fahrenheit minus 32. And then I'm just going to add 32 to both sides. Mm. And so that's how I get from one to the other. Just make sure you can do these algebraic conversions. And from there, it'll really be, so for temperature, it's really just going to be about you getting things in the right temperature and showing that, like if you were working a problem You just want to show from Celsius to Kelvin, you would want to show that you're adding 273 to the Celsius temperature. Again, notice the degree symbol for Celsius and for Fahrenheit and how it's not there for Kelvin. That's because we don't do degrees Kelvin, it's just kelvins. But a topic you're going to see show up a lot is called density. So really get in your head this basic format for density. It's the mass of a substance divided by the volume of the substance. It could be a solution, it could be like a pure liquid, a solid metal. It's just whatever substance it is. It's the mass of that substance divided by the volume. Now, I've given you the more classical representation of that. That first symbol there is a Greek letter rho. Now, in a lot of chemistry and physics textbooks that you'll find, density will be represented by rho. So I just wanted you to see that symbol so you know what you're looking at when you see it. But when we say mass times volume, it could be like I just gave you some examples here, grams per liter. Liters are volume, is a volume. Kilograms per milliliter. But also remember that your cubic numbers are volumes, grams per cubic centimeter, kilograms per cubic meter, milligrams per cubic millimeter, and so on and so forth. I really get this basic notion of density in your head so that later on, when you're solving problems, you can go, well, I have all these numbers. How do I put these all together in a way that gets me mass over volume? And that'll be density for the system. So let's look here. One metal object is a cube with edges of 3 centimeters and a mass of 140.4 grams. A second metal object is a sphere with a radius of 1.42 centimeters and a mass of 61.6 grams. Are these objects made of the same or different metals? Well, this is where you have to say, what is the problem asking us? Okay. So first off, what it's asking us, density of the cube, density of the sphere, density 1, density 2. Because those densities will tell us if it's the same metal, because density is inherent to a substance. So like if you have a block of copper metal and I have a sphere of copper metal, they should have the same densities because they're both copper. Now, what are some things that I know? Object 1. The sides of object 1 are 3 centimeters. The mass of object 1, 140.4 grams. Object 2, let's see, the radius of this sphere, 1.42 centimeters. And the mass of this sphere is 61.6 grams. So that's what I'm being asked for. These are things that I know. Okay, so I want to get each density. And notice that it says these densities are accurate to within plus or minus 1% of each other. That's going to be how we end up telling if they're the same metal. All right, so and keep in mind what I'm showing you here is just how, or is just a way to organize this problem so that each part is clear. It, you can follow what I want you to follow what I'm doing, but I also want you to just keep in mind, how can you organize your problems so that what you're doing is clear? Okay, so density 1 can be mass 1 over volume 1. That's my theorem. Okay, another theorem that I have is for a cube. 1 is going to be s cubed. So the volume of a cube is you take one of the sides and cube it. So now I can rewrite with this substitution that volume 1 is going to be mass 1 over S cubed. So now I've made my substitution and I've developed an equation that I can plug numbers into. Okay, so each side is 3.0 centimeters cubed, and it's 140.4 grams. And what I end up with is 5.20 grams per cubic centimeter. Okay, so that's the density of object 1. Let's look at object 2. This time, again, my theorem, O2 is going to be mass 2 over volume 2. However, this one is a sphere. So at some point, I may show you the integral and how to figure out the volume of a sphere, but for right now, you can look it up. The volume of the sphere is going to be 4/3 pi r cubed. So now I can make that substitution. Row 2, let's see, my denominator is 4/3 pi r cubed, mass 2. And then, of course, we have 4/3 in the denominator. So essentially, that means we're going to flip that and multiply. So the final equation that we can plug numbers into will be 3 times mass 2 over 4 pi r cubed. Okay, so then I can say, oh, so 3, your mass, 61.6 grams over 4 pi, and your radius is 1.42 centimeters cubed. And when you multiply this all up, you're going to get 5.14 grams per cubic centimeter. Now you can notice these two densities are very, very close to each other. So you start to have a sneaking suspicion that, yes, this is the same metal. But let's just take a look at that 1% tolerance. Okay, so what I'm going to do is I'm going to go back to object 1. My mass range is going to be 1% on either plus or minus 1% of 5.20. So 1% of 5.20 is what? That's what I'm trying to find here. So that means it's going to be 5.2. Let's just find out what 1% is. Times, let me do this instead, dot. And you know that 1% is actually, in its decimal form, is 0.010. I put that last zero on there to get to two significant figures. But if you want to know what the decimal number for a percent is, just take the percent and divide by 100. So 1 divided by 100 is 0.01. And I changed the time sign to a dot because I want you to remember that dots also mean multiply. Parentheses next to each other mean multiply. We'll use all of them just so you're getting used to them again. And remember that in these percentage problems, the word of is going to correlate with multiply. So now we're going to have 0.052 as my plus or minus. So that means my row 1 is going to be 5.20 grams per cubic centimeter plus or minus 0.052, which is my 1%, which means I'm going to have a range of 5.15. So 5.2 minus 0.052 grams per cubic centimeter to 5.25 grams per cubic centimeter, keeping everything in the correct significant figures. That's my range for density 1. Now, object 2. Okay, 1% of 5.14 equals what? So that's what I'm looking for now. So again, that's going to be my density 5.14 times 0.010, and that's going to give me 0.051. Okay, so density 2 is going to be 5.14 grams per cubic centimeter plus or minus the 1%, 0.051. So let's take that minus, let's take that plus. So that's going to be about 5.09 grams per cubic centimeter to 5.19 grams per cubic centimeter. And now we look. Do you notice how these two ranges overlap? So look here, 5.15 is less than 5.19. So these two ranges overlap. That overlapping tells us that yes, these two objects are the exact same metal. Okay, so that's how you answer that problem. All righty. We can also use density to solve chemical problems. Now, keep in mind, so always be paying attention. I'm going to put things, even in exercises that we work through, that you're going to want to keep in mind. Okay, so when we're talking about the periodic table, here you have a bromine molecule, Br2. Bromine is a halogen. Halogen is going to be that group 7, it depends on the periodic table you're looking at. It'll either be column 17 or column 7A. It depends on however your periodic table is labeled. Columns are called groups, and so we'll go through that quite a few times. And so your molecules, your elemental molecules of your halogens are going to be like Br2. So your fluorine molecule will be F2, your chlorine molecule will be Cl2, bromine is Br2, iodine is I2. So they're all going to take that format. But notice how at room temperature, and so room temperature is something called standard conditions, or about 25 degrees Celsius. At room temperature, bromine is a liquid. Okay? This is something to keep in mind. At room temperature, iodine is a solid. The reason this is important is because all of your other halogens are gases. Fluorine's a gas, chlorine's a gas. So you want to keep in mind your bromine and your iodine, how they're different. So at room temperature, the element bromine in its molecular form, Br2, is a liquid with density 3.12 grams per cubic centimeter. Calculate the mass of 125 milliliters of bromine, and then what volume of bromine does 85.0 grams of bromine occupy in milliliters? Okay, so this has two parts. The mass, that's part 1, and that volume is part 2. So what are some things that I know? The density of my bromine, 3.12 grams per cubic centimeter. Now, you see the question asked for milliliters, and you have a density in cubic centimeters. This is a really helpful conversion to get in your head. I know that 1 milliliter equals 1 cubic centimeter. So I can use either unit interchangeably. So it's also going to be 3.12 grams per milliliter. Let's see. For part one. Let's see. So I'm going to say my volume for part one is 125 milliliters or 125 cubic centimeters since they're interchangeable. I'm going to leave that as my list because I'm just going to work on part one. I'm going to make another short list of things I know for part two. If you want, you can put them all in your first list, just as long as you're making your list of things that you know. Okay, so my theorem is my definition of density, mass over volume. And I'm trying to find mass when I have a volume. So I'm going to multiply through by volume, which means that my mass is going to equal my density times my volume. This is just pretty straightforward algebra that we're doing right now. Okay, now I've worked through to an equation that I can put numbers into. Mass, my density, 3.12 grams per cubic centimeter times 125 cubic centimeters. It's a multiplication. Both of the 3.12 and 125 are both three significant figures. So my final answer. Now, when you multiply this up, you get 390. That's kind of an uh-oh because right now this is only two significant figures. So to make sure that I get it to 3, I'm just going to put a decimal point on it. And that's going to be 390 grams. That's the mass of 125 milliliters of this bromine. Okay, what about the volume in 85 grams of bromine? Part two, what I'm looking for. Up here for part one, I should have put what I was looking for. Okay, so now again, things that I know, my density, 3.12 grams per cubic centimeter. I still have my 1 milliliter equals 1 cubic centimeter up there, but now my mass is 85.0 grams. Let's start with my basic theorem, which is my density definition. But I'm looking for volume. So the first thing I'm going to do is multiply through by volume. And I'm going to get density times volume equals mass. But I want volume by itself. So now I'm going to divide through by density on both sides. My volume will equal my mass over my density. And now I've worked through to the equation I can put numbers into. So my volume is going to be, well, let's see, the density is 3.12 grams per cubic centimeter. My mass is 85.0 grams. And this is going to yield 27.2 cubic centimeters, which is interchangeable with 27.2 milliliters based off our identity from above. Do the units work out? So let's figure that out. Okay, so I have grams, so my volume is grams over grams per cubic centimeter. All right, so I have a fraction in the denominator, which means I'm going to flip it and multiply, equals grams times cubic centimeters over grams. We could even make this a single fraction. Grams times cubic centimeters over grams, and grams divided by grams cancels out. And I'm left with the unit of cubic centimeters, which is what I was after. Okay, so these are just some examples on how to use density. You'll see some more on your assignment. Okay, to finish off chapter 1, classifications of matter. Let's see. So one thing you'll be working with is states or phases, and that's going to be your solid, liquid, gas. The way that's represented is, if you notice at the lower corner of your molecules, so your chemical formulas, you get your phase in parentheses. So that's gas and then liquid and then solid. You'll also see them in chemical equations. This is a chemical equation called a formation equation. A formation equation is, well, we'll call it that. It's technically a pseudo formation equation because I formed 2 moles of water, but we'll talk about that. That's something we can get to much later on. But anyway, your formation equations are going to have the elements that a compound is made from coming together in the proper stoichiometric amounts to make the substance itself. So here you see the element hydrogen. H2 is the elemental form of hydrogen gas. O2 is the elemental form of oxygen gas. Those two mix to form water. But here you see the phase, the gas, and the liquid. So those are your states. You're going to be working with physical and chemical changes. A physical change, your substance doesn't change, it just changes form. And so here you see, this is called sublimation, where you go straight from solid to gas, which I would remember that because that's one of the ones that people have a hard time remembering. Sublimation is straight from solid gas. And here you see solid CO2, carbon dioxide, and it goes to gaseous CO2. So if you're wondering what was solid CO2, what's solid dioxide? It's dry ice. So this is a physical change because you have carbon dioxide at the beginning and you have carbon dioxide at the end. But chemical changes will actually change the subject, the substance. And so here, now of course, every phase, every state is gas, but this is called a combustion reaction, where you have a compound mixed with oxygen. And in this case, your combustion is of a hydrocarbon. So you see your CH4. CH4 is the chemical formula for what we call methane. Again, you'll get used to these names as we go along. So methane mixed with O2, you add heat. So we're going to put delta H there. That's a symbol you'll see in chemistry for heat is added. So methane combined with O2, and the products of the combustion of a hydrocarbon are always going to be carbon dioxide and water. So if there's a metal involved, it gets a little different. But for right now, your CH4, your methane, is what we call a hydrocarbon. It's just various numbers of carbons with hydrogens attached to them. You can have methane, ethane, propane, butane, so on and so forth. They're called hydrocarbons. And so the combustion of a hydrocarbon is always going to produce carbon dioxide and water. Now, the reason this is a chemical change is because you see that the methane and the O2, the methane molecule and the O2 molecules are taken apart and they're reformed into new substances. So at the end, we don't have methane and O2 anymore. We have CO2 and we have water. We have new substances. So the chemical molecules themselves changed into new molecules. So that's what denotes a chemical change. Let's talk about terminology here a minute. We have homogeneous and heterogeneous mixtures. A homogeneous mixture is a mixture where everything, all of the parts mix together thoroughly, and you can't tell them apart. So if you look at tap water, for example, it's not just H2O. It also has metals in it, electrolytes in it, different salts. It's all in there, but you can't see one piece or another. That's a homogeneous mixture. A heterogeneous mixture is where you can actually see and pick apart the individual pieces. So it, I don't know, think of an example, but you can see all the different parts in there. Now, I wanted to talk about these prefixes for a minute. Homo and hetero. So homo is the Greek prefix for same, hetero is the Greek prefix for different. And so you're also going to have homonuclear molecules and heteronuclear molecules. So let's take that apart. Homo, same, nuclear, same nucleus or atom. So here you have the nitrogen molecule N2. It is called a homonuclear molecule because both atoms involved are nitrogen. It's also called diatomic. Di is the prefix that means two. It's a two atom molecule. Um, don't confuse this with ammonia, which is NH3. Even though it's only nitrogen and hydrogen, well, that it's hetero, but still, um, it's not diatomic because there's four atoms involved, one nitrogen and three hydrogens. So your diatomic has to be two atoms, and that's going to be your nitrogen one, yep, nitrogen one and nitrogen two. So homonuclear diatomic. Homonuclear, same nucleus, so same atom, diatomic, two atom molecule. So uh, N2 versus heteronuclear, hetero, different, nucleus, diatomic, two atoms. Two atoms, it's a molecule made up of two atoms that are both different nuclei. So here we have carbon monoxide. So you have a carbon, you have an oxygen. So those are your heteronuclear atoms. There's two of them, heteronuclear diatomic. There's also some common things like separations of mixtures. Distillation is one. Those of you who go into organic chemistry, you will do distillation. And this is going to take advantage of the volatility of compounds mixed together in solution. So, volatility has to do with how much of a solution is in gas phase at a specific temperature. So, compounds that we call volatile, most of them are in gas phase at, say, room temperature. So, they evaporate real easy. And so, what you do in a distillation is you're going to take your solution, you're going to heat it. The more volatile compound will turn into a gas and it will separate from the other compound in the solution. That gas will go up and down into the distillation column where you have cool water or some kind of coolant on the sides, recondensing it, and then it drips out into the flask on the other side. Whereas the less volatile compound remains in the original flask. Okay, you also have chromatography. Chromatography has to do with multiple stages or phases. So it's like you have a mobile phase and a stationary phase. Here you see a paper chromatography, and you say, well, the paper is the stationary phase. The solvent is going to be your mobile phase. The solvent mixed with, in this case, the ink. The ink has different chemicals in it, has different compounds. And those different compounds are going to have a higher or lower affinity to one of the phases. They're going to the low when they have a high affinity for the stationary phase, they're not going to rise very high on the paper. When they have a high affinity for the mobile phase, so they're going to mix real well with the solvent, the compound is going to rise much higher. So you end up getting a nice splitting of these different compounds in your original sample based off their affinity for either the mobile or stationary phase. Those of you who go into biochemistry, you'll do quite a few of these with your chromatography columns. But Again, these are just some different ways to actually separate out solutions. And I don't know why it gave us that extra slide, but this is going to bring us to the end of chapter 1. So we will begin chapter 2 tomorrow. Uh, Tomorrow or the day after. It depends on when I make the video, but I'm going to make an assignment that's going to be a combination of chapter 1, chapter 2, and then and your next assignment will be a combination chapter 2, chapter 3. And next week we will end up finishing through chapter 3, which will give us then about a week to go through each subsequent chapter. So like I said, the chapters that are more straightforward, that are going to be a lot of review, we're going to do faster, and we'll take more time with the chapters that are a little more difficult as we go along. All righty, thank you.